Right as he turns off the camera.
We should have seen it last night. About 2 o'clock,
Oh, God.
Euler just turned into a sauna.
Just that room.
Like it's like a sauna in here.
No más pantalones.
Sounds dumb when you say it.
We're on chapter 9.
Brings to life.
I actually
Oh,
don't
the
know.
GRE. That's right, he's doing that today.
Oh, this is that one,
Yeah.
right? What are we doing this time?
Where did those? Okay, so we got a nice one.
Presentation might be a bit shoddy.
All right, here we go. Now we're going to talk a little bit about microstructure. That is, not just how much of each material exists, but kind of what the distribution of that material looks like, how it's distributed. So let's consider first our simple binary solid solution, like the copper nickel. And we'll take something in the center here, and we will cool it down. 1, 2, 3, 4, and 5. And we're going to look at each of those 5 points and see what we would see under a microscope if we were looking at the structure of the material. So at point 1, at T1, we would see that. Very simple. It's just all liquid. I think that makes sense. T2. This is one we talked about last time. We'd start to see bits precipitating out. Right, so solid pieces would start forming, but it's in a big sea of liquid. At T3, those pieces have now grown.
Come on, bro. Did you like it? Visitors? Visitors.
Better get that off before our presentation.
T4, right? We're mostly left with all solids. But there's just the stuff just kind of, just the liquid kind of at the grain boundaries. And things encroaching from off the camera. All right, so we just have, so all of this stuff is solid. Everything else is liquid. And then finally at T5, it's completely solidified, so now we have a bunch of grains with associated grain boundaries. And everything is solid. Just makes sense, right? Okay. Move on to a slightly more complex system, like the lead tin, the eutectic composition. Like this. We'll first go down the eutectic line. Which ones did I do? Okay. Okay. So there are all of our spots. We have 4 different temperatures and 3 different compositions.
Are we not dealing with the little triangles on the edge then?
Right now, not right now. Okay. This would be a hypereutectic or hypoeutectic rather. This is eutectic. And this is hypereutectic. Hypo below, hyper above. So at T1, they all look the same, eventually. At T2, what do you think?
Which line?
Any of them, pick one.
They're not all the same.
Right, so pick one, tell me what it looks like.
First line is a combination between liquid and what was the stuff in the left? Liquid enough.
Right, so I have little islands of alpha and a liquid matrix. This is for the, this A, B, and C. This is for A. What about C?
So we should, oh, for C. It's gonna be the same thing except with beta islands.
Right. So A and C are both basically going to look the same. The size of the islands will be different. How would I find the size of the islands? How would I find what percentages? Right, I use the inverse lever rule to determine how much of the area is alpha versus liquid. Right, make sense? For A and C, it's basically the same, and for
Doesn't that tell you mass? Is that directly correlated to area?
if it's a random cross section, right? Okay, and it would correlate directly to length too. There was a thing earlier, one of the earlier assignments was talking about grain boundaries, like average grain boundary size or something, and you had to count the number of grains in the field of view, right? Full grains and half grains. You can also do that like by drawing a line and counting how many grain boundaries I cross in a given line, and then cross that, do that dimension, so many grains per line means so many millimeters per grain, and then I can do the cross-sectional analysis that way. And so you can do it one-dimensionally, two-dimensionally, or three-dimensionally is my point. And typically you do it two, because that's what you analyze microscopically. Okay, what about the eutectic? What would it look like?
Liquid.
Right, it's going to look like pure liquid again, right? So it's going to look the same. Okay, let's look at T3. What am I going to have in T3?
Same thing as T2, except the islands be slightly larger.
Right, so now we got bigger islands. Right here, the islands are very small compared to the total length. Right? Here, the actual islands are a bigger portion of the total length. So now here at T3 for A and C, I'm going to have more like I did over here for temperature 4. Right, where the islands are going to bump up against each other, but there'll be just a little liquid left at the grain boundary region.
Is this actually like what it looks like?
Yeah, it's an artist rendering of what it looks like.
It doesn't ever like the solids are always like islands. They don't like clump together. It's not like solid on the bottom, liquid on top.
You're correct. Well, yeah. I mean, you don't really do microscopic analysis of liquid-solid mixture.
To keep it on.
Right. You'll see in a minute how we can tell.
So if you cooled something down at the eutectic line, when it became a solid, would everything be aligned?
We will see that in just a second because we have a system that's cooling down at the eutectic line. What is T3 going to look like for the eutectic?
Liquid.
Still all liquid. So now we get to the money question. No. T4A, actually we'll do B first. T4A and T4C. So what do you think B is going to look like when it goes through?
It's gonna look like one.
They don't have like the gray boundaries like that one did over there.
It will have, I'll give you that, it will have green boundaries.
But it's gonna be two different materials, right?
Right. But it's two different materials, it's A and B, this is a two-phase region, or alpha and beta. It is not a single solid solution like this was.
Right, but they all are. Is there anything different between B, A, and C?
Here, this is all one phase.
Yeah, no, I understand that. I'm saying between B, A, and C,
No,
is
there is
there
a
anything different about
There is a
the
difference.
transition? So
It's
this one would be
different.
close.
And you're not supposed to know the answer to this, I'm just making you think about it, and then I'll tell you what it is.
Alpha, like a clump of alpha and a clump of beta.
So you're like one of these is alpha, one of these is beta.
Yeah.
Right, that's not correct.
Each clump is a mixture of alpha and beta.
Each clump is a mixture of alpha and beta. What you actually get is you get this. This is the sort of generic form.
They're different.
Okay, this is the last time I'm drawing this much.
Well, you have to finish it now.
Just end with one undone.
Vertical, the last one.
One of them left undone.
Shut up.
Okay, you get that. Where the dark spaces are alpha and the light spaces are beta.
The lines like that?
Hmm?
Like, that's how like the structural lines?
Actually, yeah, it's actually plates. They're plates. But I'm slicing them in half, so I'm seeing the lines. Okay? It's what we call a lamellar structure. Lamella, anybody, biology, the little, we use the same,
Yeah.
you're just messing with it. It's a lamellar structure, okay? Because when the eutectic goes through, it has to suddenly form both alpha and beta. In reality, what happens is one of them, if it's truly a perfect eutectic, one of them will, because of some spontaneous statistically random, variation in concentration, there will be a few more of the, whatever the B material is here. Tin in this case, right? It was lead tin. There'd be a few tin atoms that might be clumped together, so boom, it would start to form a beta region. So you'd form a beta, it would solidify as a beta. But then, what would happen is, suddenly I've shifted. If I pull out a little beta, then I shift my concentration over here to the left with my liquid, right? You see what I'm saying?
Never had an actual eutectic.
So the eutectic here, as soon as I pull out a little bit of tin, then the rest of the liquid that's there, that hasn't solidified yet, shifts over and is alpha, or lead rich. And so I form a layer of alpha until it moves back to the other side of the eutectic, and then I form a layer of beta. So you see what I'm saying? As these things deposit, as a grain grows, I grow some alpha, alpha or beta, and then the thing on top of it is the opposite, because it kind of you can imagine it sort of oscillating back and forth between those two humps. See what I'm saying?
But each strip is not pure alpha or pure beta.
Each strip is pure alpha or beta, but alpha and beta are not pure lead and tin.
Right.
Right? Beta is a lead-rich tin, and alpha is a tin-rich lead.
That makes sense.
Right? Tin enriched.
So, which just means that's 10.
Right, it's tin enriched. Right, tin enriched. Right, that's what I meant. Okay, does that make sense? So it comes out this much. Now, a lot of this depends on the kinetics. If you slow it down really, really slowly, you can actually get more chunky structure. The slower you cool it, the thicker these lines get. If I cool it nice and slow, then I form a lot of beta, and then I start to switch over to a lot of alpha, and then a lot of beta. Yeah.
Did you say the T4B dark lines are alpha?
I said they're alpha because just they're thinner in this picture.
Okay.
And the alpha piece, the inverse level rule, this is smaller. So the alpha, this is more beta than alpha.
Okay.
That's why I just said that. It doesn't matter.
Okay.
Depends on how you etch it, actually. In order to be able to see this, you'd have to etch it with some kind of, something that's corrosive to one, but not to the other. Okay, yeah.
So I'm presuming this will probably, in this, I'm just wondering, is there a benefit to having large strips versus small strips?
Yes, we'll talk about it. We'll talk about it. Okay? So everybody understands. So you can also get nodular structures, or you get clumps. With it, you know, you can have a big beta thing with nodules of alpha, or you can get individual separate grains of alpha and different structures depending on how you cool it. But in general, you're more likely to get a lamellar structure, and that lamella, the layers, are going to have thickness in proportion to the slowness of the cooling. Right, so the thickness of the layer is inversely proportional to the cooling rate. That make sense? Okay, knowing that for T4B, now let's come back to T4A. Tell me what you're going to see in T4A. This picture here.
Really
Right
thick alpha
here.
lines and a little bit of beta in between?
Nope.
Clumps of alpha.
Think about what it was right before and compare it to right after. So let's even think, let's do this.
Oh, it's
Let's use it more up here.
It's clumps of alpha with beta in between.
Not quite.
Clumps
It is clumps of alpha.
And clumps of beta.
Liquid beta.
These are clumps of alpha. What's the stuff in between going to be?
Beta alpha.
It is not going to be beta. Beta alpha.
Beta and alpha.
The stuff in between, what was the stuff in between? Right here, where was it? What was the composition of that liquid? What's the composition of this liquid?
Beta and alpha.
What is the composition of the liquid that exists right here? It's eutectic liquid. Everybody see
Oh,
that?
so in between's gonna be the lines.
So in between, we have these lines. Right, so we're going to form secondary grains in here that have a line structure. So we got that, we got this, we got this. Vertical, angle, this angle. Do you see what I'm saying? Everybody understand that? Because the liquid that existed over here was eutectic liquid. So when it goes through this temperature, it behaves the same way as the T4B material. It cools as a eutectic composition.
So it's gonna be like that in every single material that has intake liquid?
Right, so everything in here or in here will have some amount of eutectic material when it cools.
Because you take out enough of one material or the other to have the eutectic ratio kind of get.
Right, so, well, what I'm saying is, you know, maybe 25% or 20% of what exists right here is eutectic liquid. That 20% behaves exactly like eutectic liquid did here. It forms these lamellar structures. And again, if you cool slowly, then the lamella are thick. If you cool quickly, the lamella are finer. Okay, but they're all lamellar.
Is it better?
And again, it can be nodular, but I'm just drawing it all as lamella so you can see it. But this could be nodular. You know what I mean by nodular? So in other words, it can be,
Nodular.
oops. Nodular would be, you know, we've got these grains, and then there's just little nodules of the other material. Okay, so there's no real preference. You can still see the grains, but there's nodules of the alpha and beta or whatever. Okay, so either of these is a possibility. This is more common. Okay? And what about T4C? What's it going to look like?
A plus beta.
Right, T4A, but all the clear grains are going to be beta instead of alpha. Okay? That makes sense?
Is it
Right.
possible to get a structure where you have crystals of just alpha and just beta?
I suppose if you went, no, because they're gonna, yeah, no. I mean, if you did, they would be very small crystals. Little small grains of alpha and beta. And generally speaking, you're gonna want to plate one on the outside of the other. Because that's, as we'll talk about next time, I think that there's a lower energy for, there's a greater likelihood of nucleating a new grain on the surface of an existing solid. And that's why when you boil your water, you can superheat water in your microwave. You guys ever done this or heard of this done? You heat water in your microwave in a really, really smooth cup. You can get the water hotter than 212 degrees because there's no nucleation sites for the evaporation to occur.
Will it explode?
For the vaporization to occur. And then as soon as you stick your spoon in it, boiling water sprays everywhere because the spoon now initiates a boiling process. You can superheat water.
Demonstration.
You have to have a really smooth.
I saw something about it, but I wasn't sure if I actually believed what they were doing.
We do last work.
So, if it's smooth enough, I guess, I don't know.
Can we try this?
I do not recommend doing this at home.
That's why we should do it.
Do not do this at
Can
home.
we do it in
in the
Euler?
lab.
Can we do it in Euler?
Can we do
Don't
it?
do it at home.
I don't want to make one of the hospitals say, Dr. Techno said good. All right.
Vegas.
Okay, are we good? Are we good on what was you put this
Water in a microwave.
process here?
So is there any way to cool it and not have a eutectic?
Is there any way to cool
Whatever you stick in it.
from in here and not have a eutectic? No.
So
Between here and here, some portion of the material is going to be eutectic.
So if you're too
But outside,
yeah.
So outside of there, so let's think about outside of there. So let's go through, let's take these two spots. And we'll look at, okay, so the liquid's boring, but you know, we'll put it up there. And we have this and this, and then we have this and this, and then we have this and this, and then we have this and this.
you can go with this, or
Five.
you can go with that. You can go with this, or you can go with that.
So, and let's call this A, B, C, this is then B, D, and E. So, D, let's do D. At T1, it's liquid, right? That's boring. We don't care about the little T1. Let's look at T2. What's T2 going to look like? Chunks of alpha. Right? I'm getting lazy now. My alphas are going to become round.
Keeping chunks.
Chunks of alpha in liquid. What about T3?
That's solid.
Solid.
Alpha enriched. Solid 10 enriched lead. Lead enriched 10.
Solid alpha, which is basically lead with a little tin in it, if this is lead tin. Right? This is all alpha.
So it's all alpha, but it's a certain concentration of alpha. Right? It's the D concentration of alpha.
Right, right. It's alpha. It's a certain concentration of tin
Yeah, but that's the
distributed throughout
thing.
the lead.
So alpha doesn't have a very good definition then.
Now, alpha is a lead with tin impurities.
Right, but so
And the concentration of the impurities is determined by where I am.
No, because impurity is based on whichever one has the most concentration.
So beta is more.
Beta is tin with, right. Beta is tin, if we're doing this in the lead tin diagram, beta is tin with some lead dissolved in it. And alpha is lead with some tin dissolved in it as impurities.
Okay, so as we move through these phases, when we have solid and liquid at once, they're at this, the solid and the liquid have the same concentration.
No. No. At this point, the liquid has this concentration,
Yeah,
the solid has
yeah, I
that
forgot.
concentration. Okay. But once we get down here, the temperature is theoretically high enough still that it kind of redistributes itself. So we don't really talk about the fact that we have, you know, more tin in this part of the, you know, so I wouldn't say I've got more tin here and a little bit less tin there. You know, I wouldn't worry about the variation in concentration of tin in that alpha. I would not, that's a level of detail we don't get into because that tin will equilibrate itself. Right, the concentration gradient will.
Okay.
And typically, if we cool slowly, right, these are equilibrium phase diagrams, then that means we have enough time there for them to re-equilibrate themselves all the way along. Okay, so now we get to T3, now with T4, what's T4 gonna look like? For D? Same, right? 3 and 4 look the same. Nothing has changed between 3 and 4. Okay? T5 is different. Let's come back to that. Let's go to E. What's T1?
Liquid.
Liquid. What's T2?
Chunks of alpha.
Chunks of alpha. Fewer chunks of alpha than we had over here at T2, right? What's T3?
All alpha.
Right, same as alpha.
But a different concentration.
All alpha. The concentration of tin in that alpha is different, but it's all alpha. Now we get to the exciting stuff. What's T4?
Well, I guess it's become some sort of like alpha with the beta alpha thing in between it. Because it's been overcome, but I really don't want.
So, what has happened when I go from here to here?
Cooled it down.
Cooled it down. But what has happened in terms of the content?
Beta.
It's moved from being pure alpha to alpha and beta, right? Where do you think the beta is most likely to form in that material?
The seams.
The grain boundaries.
Yes.
The grain boundaries. So what you get is you get the same kind of structure, and I'm going to try to draw this the same way I did the other one. But now, the grain boundary region becomes decorated with beta material. Because remember I talked about the fact that diffusivity was enhanced at the grain boundaries? Right, we could get better diffusion at the grain boundaries. But I said typically, grain boundaries represent such a small fraction of the cross-section that we don't really take that into account. Remember we talked about this? That the energy barrier for diffusion at the grain boundary is smaller? But in this case now, since I got to form some beta here, the beta is going to most readily form at the grain boundary areas where there's disorder among the atoms, and the betas can, the tin atoms can coalesce and form beta material. Okay. Typically, this begins. If I were to actually draw this, was probably more like T5. This is more of a T5. If I did this as T4, the beta would actually form primarily at the trifold, at the multiple intersections here. That's where you have the most disorder, right? When you have multiple grains meeting at a single point.
So, where is all that coming from then? Doesn't that
Diffusing.
tin come out of
It diffuses out of the lead,
So then shouldn't the lead concentration also decrease?
I mean, decrease.
Shouldn't the alpha concentrate, well, I guess it does.
All right, so the alpha concentration does drop. The amount of tin in the alpha decreases.
Yeah, right.
And as a result, beta forms at the grain boundaries.
Well, actually, no, the amount, so alpha is getting smaller, meaning the
It is getting smaller, yes. Alpha is getting smaller.
alpha is getting smaller is
It's
what
being
that
consumed.
means, right? That's what that means.
No, this means
Yeah.
that the concentration of the alpha is decreasing. The alpha pieces have less and less tin. The inverse lever rule tells you how much alpha there is versus how much beta. So the inverse lever rule, the length of this divided by the total length, tells you how much alpha. This line defines the concentration of that alpha. So the alpha is now has less tin in it. This alpha has less tin in it than this alpha did. Right, or whatever, than the alpha right before it, than this alpha. Because it's all migrated out to the grain boundaries. And again, it starts at the multiple grain, the intersections of multiple grains, and then it will spread to just the two grain boundaries, yes.
So alpha is not a constant.
No,
Okay.
alpha is a constant from here to here. I mean, all of this alpha is a constant.
Yeah.
Nothing's
So
changing.
like the term alpha.
But if I get into here,
So, at the wall, at the very left of the alpha, it's a pure lead.
pure lead, yes. Does that make sense to everybody? So you notice there is no eutectic in any of D and E, because no material ever was a eutectic liquid that crossed this boundary. And if I did the same, I could do the same thing out here in the beta region. So only between here and here do I get any eutectic material. And the closer I am to the ends, the less of this there is in the intermediate, in the spaces between the grains. Yes?
What happens if you're at the ends of the eutectic area?
Right here?
Yeah.
So in theory, then you never form eutectic. You have to be actually be inside of that grain.
Okay.
It's not likely you're going to hit
It's not
that.
like a point.
Exactly.
So back to my question earlier, to get something where you have grains of pure lead and pure tin, that would happen anywhere along the bottom line, that you're not in the corners, right? The T equals the lowest T.
Oh, right. Yeah, if you actually got out to the point where these things go to 0, yes. Right, so if you go back up to the lead tin, there's lead tin, right? But you can see, this is at 0 degrees C, there's still some tin in my lead. Right, the tin's fairly pure on that side, but there's still a little bit of tin in my lead over here. So I'd have to get off the coal in order for that to work. Any other questions?
What is this effect? Like, what actually is the effect of all
We'll
of
talk
this?
about that a little bit, strengthening. We'll talk about that in the coming weeks. Okay, but I'll make sure everybody, now a couple other language things. Dan, pay attention. Okay, so when I do my inverse lever rule here, on this one, let me do it in a different color. When I apply the inverse lever rule here, this eutectic or no, let me not use the eutectic composition. Let me apply the inverse lever rule to this. Right? So I go in there and I ask you, what's present at that point? And let's just, I'm going to make up numbers here. So this is going to be, I don't know, 15, and this is going to be, I don't have that up there anymore. Let's say this is 98. Okay? Actually, let's make this 18 and 98 then. 18 and 98. Okay? Those are the cross. So I could ask you, what do I have in this material right here? This little black dot. What's present in my material? What would you tell me?
Alpha 18 and beta 98.
Right? And say how much of each?
Well, I need to know how to do inverse level.
Let's say this is,
where A is at.
let's say this is 30. I'm just making up
So it
numbers.
would be
30 minus 18 over, is it 98 minus 18?
Right?
So that would be
12 over 80.
That'd be the amount of beta, right?
Yeah, so 0.15 equals 15% beta, right? Does that make sense to everybody?
So it's 15% 98 beta.
So 50% of beta,
Is that 50% beta in alpha?
15% beta, 15% beta, just,
Oh, so yeah, so then.
and the other 85% is alpha.
So we don't need to say what.
Now, that is an insufficient answer. If I ask you, this hypoeutectic material is cooled slowly, what do I have at that point? It is insufficient to say I have 15% beta and 85% alpha. What I have to find out what I have to consider what I had right before that transition. Right here, the green part, right, so this is now 19, and this is 62, I'm rounding. So what I have at that moment, the instant before I go through the transition, I have 30 minus 19 divided by 62 minus 19. Right, that's the left-hand side. So that's 11 divided by 43, which is, let's just say 25%, I'm approximating, is 25% eutectic liquid, right? This thing here is 25% eutectic liquid, 75%, the other 75% then is pro-eutectic alpha, before eutectic. So it is alpha that is formed before we went through the eutectic. Everybody see that?
We're talking about just above the eutectic.
The green, that's what the green, just above the eutectic. So the green stuff, right before that, this concentration, this stuff, but right before I went through the eutectic transition, I had 75% pro-eutectic alpha, I formed all these little alpha crystals. And then 25% was eutectic liquid. The instant after I go through there, so now I'm going to do blue. Right, the instant afterward, that's now 97.5. And the instant after going through the eutectic, I now have 30 minus 19 divided by 97.5 minus 19. We see that? Which is 11 divided by, what is that, 78.5. What is it? Somebody give me a number. 14% beta, which means I have 86% alpha, right? But what I really have is I have 75% pro-eutectic alpha and 11% eutectic alpha. So 11% of my alpha is tied up in these striped characters, and 75% is tied up in these big chunks. See what I'm saying? And all my beta is in these slices, is in the eutectic structure. And the reason that's important is because this stuff has different mechanical properties than this does. Pro-eutectic alpha has different mechanical properties than eutectic alpha, or the eutectic microstructure. The pro-eutectic grains have different properties than the eutectic grains. Yes, Daniel?
So for the red point that we calculated, it would be 15% beta,
Right, so
75% pro-eutectic, and 10%
percent,
eutectic?
sort of, yeah. So actually it'd be 14% eutectic, 1% would be beta it was not eutectic, it was post-eutectic.
Okay. So you start from that boundary.
So what happens is essentially, if I end up with this structure, as I continue down, somewhere beta begins to precipitate out. Right, so I start to convert some of my material into beta, so I end up with nodules of beta growing, nodules of pure beta growing in here, at places where it's preferred to do so.
So that would be like where like a bunch of green boundaries would be more likely.
Right, right. Okay. So it can be much more complex than just inverse level rule.
So we're going to.
So you have to walk yourself through it one step at a time. So let's do an example. Calculate the amount of pro-eutectic gamma So there's the word proeutectic. Calculate the amount of proeutectic gamma that is formed at 1,000 degrees C in the slow cooling of 100 kilograms of 3.8% carbon white cast iron. So you have a large percent carbon, it's cast iron. Right, so steel is generally stuff down here. When we get to larger percents carbon, it's cast iron. Gray cast iron or white cast iron are the two kinds of cast iron. We'll talk about those later. And also determine the total amount of gamma in this material. So basically they're asking, what is the amount of proeutectic gamma and the amount of total gamma? Does everybody understand that? So we start out 3%, 3 weight percent. Right, that's right here. That line. So how would I find the amount of proeutectic gamma?
Back that up to 1,148.
Right, go to just above the eutectic temperature, 1148 plus. And at 1148 plus, just drawing that little section that matters to us, right? We got this thing coming up here, and this thing doing this, the gamma doing this, right? And we're at 3%, which is pretty close to being in the middle, not quite. Right, this is where we are. So we want to evaluate it right above the eutectic temperature. We know that this point here is 4.3. We know that this point here is 2.11. 2.11. And this is 3. That make sense to everybody? I got those numbers? So I want to find out the amount of gamma. What do I do?
4.3 minus 4.3 minus 2.11.
We see that? It's the inverse lever rule, so use this side to find out how much gamma. Okay? So that becomes 1.3 divided by 2.19, which is 59.4%. And since they conveniently gave us 100 kilograms, 59.4 kilograms of proeutectic gamma, proeutectic austenite. That's the chunks, 59.4 kilograms of chunks distributed throughout the whole material. Right? Now, what's the total amount of gamma in this material? What would I do to find the total amount of gamma in this material?
Just do the inverse level rule at the operating point?
Right, the operating point here is 1,000, so I'm going to come down to this line, right? So I need to define the ends of my line. That line, that end, we know is 6.69. Right, the cementite end is always 6.69. This end is conveniently 1.5. So now, I'm down here in this region. Well, this is at 3. This is at 1.5, and this is at 6.69. And I want to find the total amount of gamma. So what do I do?
Same thing, just 6.69 minus 3 over 6.69 over minus
1. 3.69 divided by 5.19, and I don't have that number. Somebody got it? .711? So 71.1 kilograms. So at 1,000 degrees, right, I have this chunk of proeutectic material, and then an additional gamma that is formed after the eutectic. Right, that's buried in the lamellar structure. Now, there's been some diffusion of those things, but go ahead.
So
Between
that is our total.
That is the total gamma, 71.1 kilograms of gamma
And 59.4 kilograms of that is
proeutectic. Is proeutectic.
And the rest of it is cementite.
No, the rest, oh, you mean the other 29 or 28.9
Yeah.
kilograms is then cementite. And all the cementite would be in a eutectic composition, a eutectic microstructure. Right, the only place I get, when I drop down here at 3%, the only place cementite ever forms is in the eutectic. So 100% of the cementite is going to be in the eutectic.
Will
Structure.
cementite ever not be eutectic?
Will cementite ever not be eutectic? Not in the part we care about. We don't work on the right-hand side of it. You'll never go to the right.
Okay, so even
We'll
that
stay on the left side.
liquid plus cementite, that cementite is still eutectic cementite, or?
Oh, I see. If you go on the right-hand side, I thought you meant for the 3% composition. If you go to the right of 4.3, then you can have cementite that is not eutectic.
Okay, yeah, I think in general.
Yeah, so you can have non-eutectic cementite above 4.3%. Yeah.
Can you just go through and say the answer? And it's like 59.4 kilograms per eutectic austenite.
Right.
71.1 is
Total austenite.
okay. And then what else from that do we need to answer the question?
That's it. That's all.
Oh, that's all.
So ask for the amount of proeutectic austenite and the total austenite. Okay. And what will really happen is, as this thing, so you form something that looks like this, right? Proeutectic austenite, so it would be gamma instead of alpha, and then the eutectic material in between. And then as we continue to go down, some of this stuff will sort of dissolve away, and what will happen is the amount of cementite will increase, and so you'll get diffusion of carbon along the grain boundaries, and so you'll form cementite along the grain boundaries like this. So the proeutectic alpha will actually be eaten away. Some of that proeutectic alpha will be eaten away. As you can see, I move from here down to here, down to here, right? The concentration of my alpha is going to decrease in the amount of carbon. It's going to go from 2.11% carbon in my alpha down to 1.5% carbon in my alpha. That additional carbon is going to diffuse out to the grain boundaries and form cementite at the grain boundaries. That make sense? Okay, well, we're out of time. I won't do my next problem. It's too bad, because the next one's lead tin would have been maybe. All right, so a lot of microstructure stuff there. Try to make sure you understand what's going on. And next we'll talk about the kinetics of how that forms, the time, how the time impacts this, the cooling rate. And then from there we'll talk about the mechanical properties that result in those different factors. Dan doesn't want to stare at Clayton any longer than he has to. Hold on.